much for the kind introduction. And I am Kiyotaka Nakajima from Hokkaido University. So my talk is about the Niobium-based solid acid catalyst for smart biomass conversion. So first speaker, Andre, introduced the concept for the reduction of the CO2 emission, and our study to utilize biomass for chemical production is contributing to the decarbonization of our society. So, biomass is now recognized as a renewable feedstock for the production of chemicals and energy. And biomass mainly contains three components. And for example, cellulose biomass contains cellulose, hemicellulose, and lignin. And we have to utilize these three components for chemical production. And when we hydrolyze the cellulose to glucose, this is the first molecule to be utilized for the chemical production. After the dehydration of glucose, so we can get HML as shown here. This is an aromatic component with two functionalities, hydroxymethyl group and formyl group. And this is an attractive molecule for chemical production because we can convert these two functionalities as we like. For example, we convert these two functionalities to carboxylic acid, amine, and the diol. We can utilize this molecule for polymer application. And when we remove the oxygen molecule from this one to synthesize dimethyl alternative, this can be utilized as fuel additive. And here this slide contains several concepts for the utilization of ATMF in polymer application. So we can convert these two functionalities like this carboxylic acid, diol, amine, and we can obtain the furan-based or aliphatic-based monomers utilized for the polymer application. These are the replacement of the oil-based monomer as shown here, mainly obtained from fossil fuel resources. So in this presentation, we focus our attention on the furan dicarboxylic acid, this molecule. Furan ring have two carboxylic acid. This is the alternative of this is the potential replacement of the terephthalic acid. The terephthalic acid can be widely utilized for polymer chemistry. So polymerization of ethylene glycol with terephthalic acid produces polyethylene terephthalate. This is a very famous polyester, mainly utilized for the beverage bottle application. And if we replace this oil-based terephthalic acid with biomass-based furan dicarboxylic acid, we can obtain polyethylene furanate as shown here. Polymerization of ethylene glycol with this molecule produces this kind of polyester. This is a potential replacement of the oil-based ethylene, the PET. And I have to introduce very attractive feature of this polymer. So the resulting polymer, polyethylene furanate, have excellent gas barrier property. And this molecule is recognized as the high gas barrier polymer. So for example, this polymer has high gas barrier property to oxygen, CO2, and water compared to the petroleum-based PET. And in addition, attractive tensile strength as well as the excellent thermal properties for processing make the polymer much more useful for the common chemical industry. And potential application of this polymer is the beverage bottle, of course, and film, carpet, and so on. And total amount of terephthalic acid consumed for the PET and PBT production in Japan is about more than 14 million tons in a year, with an annual growth rate of still 6.9%. This means that if we replace all the terephthalic acid consumed for the polymer production with this attractive molecule, we can contribute to the reduction of CO2 emission. So due to the potential application of this monomer, so a lot of research group as well as the industrial companies, so focusing the attention for the development of this monomer production process. And I have introduced one example organized by EU consortium. So this is preference project organized by EU. So this was organized under the European Union Horizon 2020 and with a very huge grant as shown here. The purpose of the project is to build the flagship plant for the production of purified FDCA, the monomer of PEF, and demonstrate and validate at least 100 bio-based material in the end-use application, and commercialize these 100 bio-based end product and demonstrate it in the project, and demonstrate and optimize the new local bio-based value chain from raw material sourcing to PEF end product, and evaluate environmental and the socio-economic performance of the developed product. This is a very challenging project, and everybody expected the accessibility, high accessibility of the PEF material from this project. But this project unfortunately failed in. And as a result, so the availability of the PEF in EU is still 0.0% as shown here, according to the Global Production Capacity of Bioplastic 2020, released from the European Society. So although the several important bio-based molecules, for example, PLA or bio-based PE or PP, is the increasing the amount. It's with the amount. So again, I want to review the process how to obtain the furan dicarboxylic acid, this target molecule from biomass. Cellulose is the main source for this production, and the acid catalyzed hydrolysis of cellulose produces glucose in the first step. And glucose is involved in the acid catalyzed dehydration to produce HMS as shown here via fructose. And finally, aerobic oxidation of this HMF produces furan dicarboxylic acid. This process mainly contains three important elementary steps as shown here, and two of them are related to acid catalyzed reaction. And in the latter part of my talk, I will introduce Niobium technology for the acid catalyzed dehydration glucose to HMF. This is the bottleneck issue in the entire process. So first of all, I have to introduce the acid property of niobium oxide. Hydrated niobium oxide is recognized as a niobic acid. This material was reported by the Professor Kozo Tanabe. He is Professor Emeritus at Hokkaido University. Unfortunately, he passed away several years ago, but according to his great achievement, will affect a lot the research activity of biomass conversion using heterogeneous catalyst. He found out niobic acid is a strong brassic acid catalyst with its acidity comparable to an aqueous 78% H2SO4 sulfuric acid solution. This is really strongly acidic. And niobic acid is one of polyol acid, isopolyol acid, as shown here, with brassic acidity and loose acidity. And niobic acid has brassic acidity as well as the loose acidity, this one, and both of them are very effective for sugar conversion. And the solid catalyst is very important for the future sustainable chemical production, because when we use sulfuric acid in chemical production, it is a homogeneous mixture of the product solution and the acid catalyst. It's hard to isolate the acid catalyst only from the reaction mixture. If we have solid, strong acid catalyst, for example, strong sulfuric acid, cheap, high acidity, and high stability, they're safe for handling. For example, if we have niobic acid on my hand, nothing happens. But if we add the sulfuric acid on my hand, it is injured. My hand is injured. So safety for handling is the very important factor for sustainable chemical production. And if we add this kind of solid acid in the reaction mixture, and reaction started. And finally, after the reaction, the catalyst is easily separated from the reaction mixture as shown here. Decantation will give us solid precipitate at the bottom of the reactor. And finally, we can remove this reaction mixture by simple filtration, and subsequent addition of the reaction mixture again to the remaining catalyst will start the next reaction. So if we guarantee the high reusability, we can repeat the same reaction system without separation of the catalyst. So this is one example what the importance of the solid acid. When we use sulfuric acid, for example, acid catalyst, we can precipitate this, so the acid catalyst by neutralization reactions here. Finally, we can recover the sulfuric acid as a neutralized salt. It is no longer acid catalyst. And the neutralization produces 1.4 kilogram of sodium, for example, sodium sulfate acid waste from 1 kilogram of the sulfuric acid. Sulfuric acid produces more and more acid waste. So in this sense, we have to find out solid catalyst for the chemical process. And our group found that the niobic acid with the Lewis acid site can work for the selective conversion of glucose to HMF in water. So people recognize the niobic acid has Lewis acid site, but they didn't pay attention for the water tolerance Lewis acidity of this one. Our finding is based on this one. The Lewis acid catalyst can work in water for sugar conversion and to produce HMF from glucose. And the activity of niobium acid is not so much high compared to HCl, H2SO4, and some typical zeolite material, but this finding contained very important concept for the Lewis acidity to be utilized for sugar conversion. And this concept can be extended to other sugar conversion reactions. And we examined another sugar, xylose, obtained from hemicellulose to obtain the furfural. This furfural is very attractive for the production of furfuryl alcohol, furan and furfural, and also the one for butanediol and succinic acid. And conversion of xylose to furfural can be achieved on the niobium acid. I mean, the Lewis acid site of niobium oxide can convert this molecule to furfural smoothly. And the furfural formed in the water phase is extracted smoothly with toluene to prevent the byproduct formation. And this catalyst show high activity, and these results show the activation energy. Niobium acid have the low activation energy compared to the sulfuric acid and HCl, meaning that furfural conversion can be achieved at low temperature very smoothly. And also high reaction rate of the niobium acid indicate the applicability of this material for mass production. And this is the final example to utilize niobium-based solid catalyst for biomass conversion. You know, lactic acid is one of the very important molecules for the sustainable chemical development in the future, because this can be utilized as a monomer for biodegradable polymer. Current PLA production in Japan is around 4,000 million ton in a year, but it is growing. So the trial sugar, as shown here, can be obtained from both glucose and the glycerol. These both are the biomass-derived molecules. And acid catalyzed dehydration and hydride transfer can be achieved with the niobium-based solid acid catalyst. and we will obtain lactic acid. We find the new niobium oxide-based solid catalyst. So niobium oxalate, hydrothermal treatment of niobium oxalate produces a deformed orthorhombic niobium oxide. This material have pentagonal unit. This is very unique, connected to each other by octahedral unit, and the forming six-membered ring of the microportion here. This structure guaranteed high surface area compared to the amorphous niobium oxide, and this material have a lot of acid site compared to niobic acid, and this material shows the high activity for this reaction. Okay, let's summarize my talk. So the utilization of renewable carbon source is the key factor to establish the sustainable society in the future. So catalytic technology using heterogeneous catalyst, mainly focusing on the niobium oxide, is very important for sustainable chemical production. Continuous studies for unique catalysis of niobium material is important for biomass conversion. And I have to announce that we have very good friendship with CBMM and Sojitz. So our society, Catalyst Society of Japan, will organize the reference catalyst the network, so our membership can receive these material from the society and utilize them for the acid catalytic reaction. So the sustainable development may be based on the continuous friendship between Japan and Brazil. And finally, I have to thank all the collaborators in my research group. I'm belonging to the Fukuoka laboratory at the Institute for Catalysis, Hokkaido University. And I have to thank also for the financial support from GST and the JSPS. And thank you very much for your kind attention.